TCP and how it came about, and then move on to the descriptions of the technical goals defined by the original designers. Then you'll get a look at how TCP/IP compares to the theoretical model, the Open Systems Interconnect OSI model, TCP/IP Design Goals. When the US Department of Defense began to define the TCP/IP network goals, their design goals include the following. TCP/IP had to be independent of all hardware and software manufacturers. Even today, this is fundamentally the way TCP/IP makes good sense in the corporate world. It's not tied to IBM, Novell, Microsoft, DEC, or any other specific company. It had to prove good built-in failure recovery. Because TCP/IP was originally a military proposal, the protocol had to be able to continue operating even if large parts of the network suddenly disappeared from view, say after an enemy attack. It had to be able to handle high error rates and still provide completely reliable end-to-end service. It had to be efficient and have low data overhead. The majority of data packets using the IP protocol have a simple 20-byte header, which means better performance in comparison with other networks. A simple protocol translates directly into faster transmissions, giving more efficient service. It had to allow the addition of new networks without any service disruptions. As a result, TCP/IP was developed with each component performing unique and vital functions that allowed all the problems involved in moving data between machines over networks to be solved in an elegant and efficient way. Before looking at both TCP and IP particularly, you should understand where TCP/IP fits into the broader world of network protocols and particularly how it compares to the theoretical reference model published by the International Organization for Standardization (ISO) at the OSI model. The Transmission Control Protocol. Transmission control Transmission Control Protocol (TCP) is the transmission layer of the protocol and serves to ensure a reliable, verifiable data exchange between hosts on a network. TCP breaks data into pieces, first wrapping it with the information needed to route it to its destination and then reassembling the pieces at the receiving end of the communications link. The wrapped and bundled pieces are called datagrams. TCP puts a header on the datagram that provides the information needed to get the data to its destination. The most important information in the header includes the source and destination port numbers, a sequence number for the datagram and the checksum. The source port number and the destination port number ensure that the data is sent back and forth to the correct process running on each computer. Sequence number allows the datagrams to rebuild in the correct order in the receiving computer and does by first totaling the contents of the datagram and inserting the number in that header. This is when IP enters the picture. Once the header is in the datagram, TCP passes the datagram to the IP to be routed to its destination. The receiving computer then performs the same calculation, and if the two calculations do not match, an error has occurred somewhere along the line. The datagram is resent. The following figure shows the layout of a datagram with the TCP header in place. So here's the datagram. It shows source port, destination port, sequence number, DO, reservation, flags window, checksum, urgent pointer, and options. In addition to the source and destination port numbers, the sequence number and the checksum A TCP header contains the following information. Acknowledgement number indicates that the data was received successfully. If the datagram is damaged in transit, the receiver throws the data away and does not resend an acknowledgement back to the sender. After a predefined timeout expires, the sender transmits the data for which no acknowledgement was received. Offset specifies the length of the header. Reserved variables set aside for future use. Flags indicate that the packet in this end of the data or that data is urgent. Window provides a way to increase packet size which improves efficiency in data transfers. Urgent pointer gives the location of urgent data. Options a set of variables reserved for future use or for special options as defined by the user of the protocol. Padding ensures that the header ends on a 32-bit boundary. Internet Protocol. The network layer portion of TCP IP is called Internet Protocol. IP is what actually moves the data from point A to point B, a process that is called routing. IP is referred to as connectionless, that is, it does not swap, control information, or handshaking information before establishing an end-to-end connection and starting a transmission. The Internet Protocol must rely on TCP to determine that the data arrived successfully and its destination and retransmit data if it did not. IP's only job is to route the data to its okay. The only job okay. IP's only job is to route the data to its destination. In this effort, IP inserts its own header in the datagram once it received from TCP. The main contents of the IP header are the source and destination address, the protocol number, and a checksum. Without the header provided by IP, intermediate routers between the source and destination, commonly called gateways, would not be able to determine where to route the datagram. Field, the fields in the IP header include the following. Version defines the IP version number. Version 4 is the current standard, and values 5 or 6 indicate that special protocols are being used. IP version 6 is currently supported by the newest equipment and is quickly becoming the new standard. IHL, Internet Header Length, defines the length of the header information. The header length can vary. The default header is 5 32-bit words and the fifth word is optional. TOS, type of service, indicates the kind of priority of the required service. Total length specifies the total length of the datagram, which can be a maximum of 576 bytes and a maximum of 65,536 bytes. Identification provides information that the receiving system can use to reassemble fragmented datagrams. Flags. The first flag bit specifies that the datagram should not be fragmented and must therefore travel over subnetworks that can handle the size without fragmenting it. The second flag bit indicates that the datagram is the last of a fragmented packet. Fragmentation offset indicates the original position of the data and is used during reassembly. Time to live originally. The time in seconds that the datagram could be in transit. If this time was exceeded, the datagram was considered lost. Now interpreted as a hop count. and usually set to the default value of 32 for 32 hops. This number is decremented by each router through which the packet passes. Protocol identifies the protocol type, allowing for the non-use for allowing for the use of non TCP IP protocols. A value 6 indicates TCP and the value 17 indicates user datagram protocol UDP. Header checksum, an error checking value that is recalculated at each stopover point necessary because certain fields change. TCP header, the header added by the TCP part of the protocol suite. So this is just an illustration of what I've taught here. Our version IHL TOS total length identification flags fragmentation offset, time to live protocol, header checksum, TCP header, and start of data. So I'm going to leave it here today for this video. If you enjoyed listening, please consider like, sharing, or subscribing. And thanks again for listening.